In this video, we start part one of testing a claim about a proportion. Here, we're talking about two of the three normal approximation methods. In learning outcome number one, we're going to talk about the p-value and critical value methods. And learning outcome number two, we're going to talk about confidence interval methods and how those are different from the p-value and critical value methods. Specifically in this learning outcome, we're going to describe the requirements for the normal approximation methods. We did not touch on this in 8.1, although we did touch on the rest of this learning outcome. So a lot of this is going to seem familiar to you. But first we'll talk about the requirements for using this normal approximation. And then we're going to test a claim about a proportion using the normal approximation to the sampling distribution of the sample proportions, using both the critical value method and the p-value methods. So here's a review of notation. Remember, lowercase n is the sample size. Now, if we're thinking of this as a binomial distribution, or we're thinking of this as having a binomial distribution, the sample size is the same as the number of trials. P is the population proportion. We can think of that as the probability of success in one trial. This is the value of P used in the null hypothesis. P hat is the probability of success in our sample. So this is the proportion of trials that were successful. So if there are X successes in N trials, P hat is just X divided by N. And Q hat, or it's not Q hat, but just Q, is the probability of failure in one trial, given that the null hypothesis is true. In that case, Q is just 1 minus P. So here are the requirements. First, our sample observations need to form a simple random sample. Now, back in chapter 1, we talked about simple random samples and random samples. We didn't get into too much of the nitty-gritty about the difference between those two, but you may want to review that if you're going on to more statistics classes, or if you are in a field that requires a lot of statistics. You might need to know the difference between a simple random sample and a random sample. So I would go back and review that. Now, for our purposes, if you see the word random in the problem statement, usually in reference to randomly selected values or randomly selected participants or randomly selected something, or you even see a random sample mentioned in the problem statement, we will assume that this first requirement is met. The next requirement is that the conditions for a binomial distribution are satisfied. There must be a fixed number of trials. Now, if we know our sample size and we think of each value in our sample as being a particular trial, this will automatically be met because the sample size and number of trials are going to be the same thing. And then every trial would have exactly two outcomes. We typically call those success and failure. Third, the trials need to be independent from each other. What that means is the probability of success or failure in a given trial cannot at all depend on the probability of success or failure in any of the other trials. And then lastly, we're assuming that the probability of success remains the same in all trials. If there's some reason to believe that that's not true, we shouldn't do this. Most of the time, we're not given that information, but we would assume that that is true. And then the last requirement is that n times p must be greater than or equal to 5, and n times q must be greater than or equal to 5. Now, on the surface, it looks like that's not particularly meaningful, but remember, n is our sample size, or the number of trials, and p is the probability of success in one trial, provided that the null hypothesis is true. So if I'm taking the number of trials and multiplying by the probability of success in one trial, that's giving us the number of successes. So when they say that n times p has to be greater than or equal to 5, what we're saying is that the number of successes that is expected for n trials, given that the null hypothesis is true, must be greater than or equal to 5. Now, q is the probability of failure in one trial, given that the null hypothesis is true. So n times q here is the number of failures. So here we're saying that that number of failures has to be greater than or equal to 5. And that's the expected number of failures given that the null hypothesis is true. Okay, so if the number of failures and the number of successes are both greater than or equal to 5, then the sampling distribution of the sample proportions can be approximated by a normal distribution with a mean equal to that population proportion in our null hypothesis and a standard deviation equal to the square root of p times q over n. Now, sometimes you'll see this written differently. They will say, this condition is sometimes written this way: n times p must be greater than or equal to 5, and n times q must be greater than or equal to 5, so that the binomial distribution can be approximated by a normal distribution. It's the same thing. They have a slightly different mean and a slightly different standard deviation, but we can see that through some algebraic manipulation, if one of those is normally distributed, then the other one is normally distributed. So we're going to focus on the sampling distribution of the sample proportions instead. Okay. Now, the value of the test statistic, the p-values and the critical values, are the same in this video as they were in lesson 8.1. So I'm just going to review those terms with you here. The test statistic will be given by z, and this corresponds to our sample statistic, in this case, a sample proportion, p hat. This is the z-score associated with p hat, provided that the sampling distribution of p hat is approximately normal with this mean and this standard deviation. In other words, it's the number of standard deviations that p hat is above or below the mean, provided that the null hypothesis is true. This test statistic will allow us to see if p hat is significantly high or significantly low by looking at whether the test statistic is significantly high or significantly low. And then p-values are the corresponding probabilities. So these are probabilities or areas in the tails beyond that test statistic z. We can compute these probabilities using Excel or Table A2 or other forms of technology. And critical values are values of z that separate the typical values of the test statistic from those that are significantly high or significantly low. Now, critical values that are associated, or excuse me, test statistic values that are sort of typical are associated with p-hat values that are typical. And test statistics that are significantly high or significantly low are associated with p-hat values that are significantly high or significantly low. So these critical values are z-scores, but they separate the values of the test statistic z and the sample proportion p-hat that are typical, given that the null hypothesis is true, from those that are significantly high or low. Now here is the procedure for hypothesis testing. Both the critical value method and p-value methods start with the same 4 steps. We're going to start by writing the claim in symbolic form and then using that to infer the null and alternative hypotheses. Then we're either going to identify the sample statistic from the problem statement or compute the sample statistic in the problem statement by taking the number of successes and dividing by the number of trials. And we want to identify the sample size as well. Then we want to graph a sampling distribution of the sample statistic, assuming that the null hypothesis is true. That's going to give us the mean of that sampling distribution. Then we also want to label the sample statistic on the graph. And the question to ourselves becomes, is that sample statistic significantly high or significantly low, given that the population proportion is whatever it is stated to be in the null hypothesis? In order to figure out if that sample statistic is significantly high or significantly low, we find the corresponding test statistic, which is a z-score. It's going to give us the number of standard deviations p-hat is above or below the mean on that sampling distribution, assuming that the null is true. Okay, then the p-value method and the critical value method, they diverge right here. So on this slide, we're going to go through the rest of the hypothesis test using the p-value method. In the p-value method, we're going to make a decision about the null relative to our desired significance level. And the first thing that we'll do in order to compute the p-values is classify the test as a two-tailed test, a left-tailed test, or a right-tailed test. Then we're going to find the p-value. This is the area in the tails beyond that test statistic. If the test is two-tailed, p is double the area in the nearest tail. So we're going from the test statistic to the nearest tail, and then we double that area. If the test is left-tailed, p is the area in the left tail beyond the test statistic. If the test is right-tailed, p is the area in the right tail beyond the test statistic. And then we're going to make a decision. If p is less than or equal to alpha, remember what p is. These areas correspond to probabilities. Then what we're saying is the probability of getting a test statistic that is as high as our test statistic, or higher if it's in the right tail, or as low as our test statistic, or lower if it's in that left tail. If that probability is less than or equal to alpha, which is our significance level, then we're going to say that that value of this test statistic is significantly high or low. So we're going to reject the null hypothesis, which led to that probability. We're going to say, if this is supposed to be extraordinarily rare, but it's happening, well, then the assumption that led to us saying that that is rare must be false. So let's reject the null hypothesis. That's going to be sufficient evidence for us to reject the null hypothesis. Now, if p is greater than alpha, then the value of the sample statistic that we have is likely to occur, or could easily occur by chance, or could easily occur due to chance, given that our null hypothesis is true. Now, we can never accept the null hypothesis. We can never prove that the null hypothesis is true. But we can say there is not enough evidence to reject this null hypothesis. So we're going to fail to reject the null hypothesis. And then after all of that, we're going to state our final conclusion about the original claim in non-technical terms so everyone can understand us, even if they don't know what p-values are, what p is, or alpha, or z-scores, or t-scores, or even null and alternative hypotheses. They don't need to know that. We're going to state a claim in words that everyone can understand, or state our conclusion about the claim, in words that everyone can understand at the end of any hypothesis test. So that's the p-value method. Now let's look at the critical value method. Now we still have to determine whether that test is two-tailed, left-tailed, or right-tailed. Once we know, we want to sketch that distribution, that sampling distribution of the sample proportions, and then we want to shade that critical region. So you can do that with the sampling distribution of the sample proportions, or you can do that with the converted standard normal distribution. And then we want to find the critical values. Those are the z-scores that separate the area in that left tail if it's a left tail test, or the right tail if it's a right tail test, or that area in the two tails if it's a two-tailed test. And those areas in each case are going to have a total area of alpha. We're going to have the critical values are z-scores that separate that alpha area in the tails from the values of the test statistic that we're going to consider typical or expected given that the null hypothesis is true. And of course, all of this is relative to a desired significance level alpha. And then we're going to make a decision. Now remember, with the critical value method, we're comparing z-scores. So we're going to compare critical values of z to a test statistic, which is also a z-score. If the test statistic lies in the critical region, which means that the absolute value of that test statistic is greater than the absolute value of the critical z-value, then it's farther out in the tails than those critical z-values are. So that means that the test statistic corresponds to a value of the sample statistic p-hat that is significantly high or significantly low. And since it's so improbable that happens, given our assumption, but then it's happening, we're going to reject the assumption, which is rejecting the null hypothesis. Now, if our test statistic does not lie in the critical region, so if it's sort of close to the mean, if we were to look at that sampling distribution of the sample proportions. Or close to the mean if we're looking at that converted standard normal distribution. Then we're going to say this value of the test statistic, which corresponds to a value of the sample statistic, could easily have occurred due to chance, given our assumption. So we cannot accept the null, but we can fail to reject the null in that case. We can say that we don't have enough evidence to reject the possibility that the null hypothesis is true. And then we'll want to state our conclusion in terms everyone can understand. Okay, so now let's do an example. We're going to do this example with both methods, both the p-value method and the critical value method. It says, in a study of 1,228 randomly selected medical malpractice lawsuits, it was found that 856 of them were dropped or dismissed. Use a 0.01 significance level to test the claim that most medical malpractice lawsuits are dropped or dismissed. Now, in order to do that, there's a lot that we need to compute and a lot that we need to think about. So if you're doing homework in MyLab Statistics, you're going to see something that looks like this. They're going to ask you to identify the null and alternative hypotheses, the test statistic, possibly the p-value, possibly the critical value or values. If you have a two-tailed test, you'll have two of them. And then we'll want to state a conclusion about both the null hypothesis and a final conclusion that addresses the original claim. First, we want to use the p-value method, and then we want to show that we're going to get exactly the same result using the critical value method. In both cases, we want to use that normal approximation to the sampling distribution of the sample proportion. Okay, so let's get started. First, we need to check the requirements. Well, we were told that those 1,228 lawsuits were randomly selected. And next, we need to check that the requirements for the binomial distributions are met. So first, we have a fixed number of trials. There's 1,228 trials. They're independent trials. The outcome, or whether or not a lawsuit was dismissed or pursued in one trial, is completely independent of whether that lawsuit was dismissed or pursued in the other trials. In every trial, or in every lawsuit, is either dismissed or pursued. So there are two categories, one which we'll call success and the other one which we'll call failure. And then we don't know this for sure, but we can assume that the probability of dropping a lawsuit is the same in every trial. Now, if the null hypothesis is true, so that means the true population proportion is 0.5, which means half of medical malpractice lawsuits are dismissed, and the other half are pursued. If that's true, and we have 1,228 lawsuits, well, then we would expect 614 of them to be successes and 614 of them to be failures. Well, it's definitely at least 5 successes and at least 5 failures. So that's satisfied, which means that the normal approximation to a binomial distribution is appropriate, which also means that the normal approximation to the sampling distribution of sample proportions is appropriate. Okay, so now let's start our hypothesis test. First, we will identify the null and alternative hypotheses. First, we look at our problem statement, look for the claim. The claim was that most medical malpractice lawsuits are dropped or dismissed. In symbolic form, the word most means the majority, or in other words, the proportion is greater than 50%, but we want to write that in decimal form. So we'll say that P is strictly greater than 0.5. Now, after we write the claim in symbolic form, we always want to write the statement that would be true if the claim isn't true. So if P is not strictly greater than 0.5, then P would have to be less than or equal to 0.5. So now when we're identifying the null and alternative hypotheses, we look at these two, and we look for the one that does not contain the condition of equality. Well, this one right here has a strictly greater than sign. So P is not allowed to equal 0.5. So this is our alternative hypothesis. It's a little bit hard to write. So that's that there. The one without the condition of equality is the alternative. And then the null hypothesis always looks exactly like the alternative hypothesis, except you change that sign to an equal sign. The null always has an equal sign. So we'll have p equals 0.5 here. That's what we're going to test against. Okay. So after that, you want to either identify the sample statistic from the problem statement or compute the sample statistic from the problem statement. And then we want to identify the sample size n as well. So here's our problem statement. It says, in a study of 1,228 randomly selected medical malpractice lawsuits, it was found that 856 of them were dropped or dismissed. Okay, so that's going to be enough to give us our p hat. I'm sorry, guys, I'm having a little bit of trouble with my cursor again tonight. So I've got 1,228. Well, it's okay. Lawsuits, and 856 of them were dismissed. So for thinking of a lawsuit that is dismissed or dropped as a success, p hat is the number of successes, which is 856, divided by the total number of lawsuits, which is that 1,228. Now, if we evaluate that, just use your calculator, we find that that is approximately 0.697. And the sample size is 1,228. Okay. Now we want to graph the sampling distribution of the sample statistic p hat, assuming that the null hypothesis is true, and label the sample statistic on the graph. This isn't a necessary step, but it helps us visualize exactly what it is we're doing and why we're doing it. So our null hypothesis is that the true proportion is 50%. So half of medical malpractice lawsuits are dropped or dismissed, and the other half are pursued. P hat turned out to be approximately 0.697. So if I draw my distribution of the p hats, and remember how this is constructed, we're looking at all samples of size 1,228. And every time we select a sample of size 1,228, we compute a p hat. And then we select a different sample of the same size and compute a p hat. And we do that again for all of the possible ways that we could select a sample of size 1,228. And then we look at the distribution of the p hats. Well, because our requirements were met, the sampling distribution of the p hats is approximately normal. And we know from our studies of section 6.3 that the mean of the p hats is that population proportion p. Remember, p hat was an unbiased estimator. Now, in our assumption, the null hypothesis tells us that p is equal to 0.5. So now we're assuming that the null is true. So we know the mean of the p hats is equal to p, which is equal to 0.5. And we're asking ourselves, if that's true, is this p hat, which is approximately 0.697, significantly high or significantly low given that assumption? If it is significantly high, we want to throw out the null hypothesis because something that is supposed to be rare is actually happening, so our assumption must be false. That's the rare event rule. But if p hat is sort of typical, given that the null hypothesis is true, then we want to say we can't reject the null. We'll fail to reject the null. We don't have enough evidence to reject the null, but we have to leave the possibility there that the null could be true. Okay, so we've got our sampling distribution of the sample statistic, and the question is p hat significantly high given that p is equal to this value and we have a sample size of 1,228. In order to determine whether p hat is significantly high, we're going to convert p hat to the corresponding test statistic. That's just converting from this non-standard normal distribution, or this approximately non-standard normal distribution, to a standard normal distribution. Okay, so in order to do that, we're just looking at that, and we want to convert to a z-score. So instead of having a mean of p equals 0.5, we want to convert to a z-score, which has a mean of 0 and a standard deviation of 1. And our question is, what is the z-score that corresponds to this p hat, which is approximately 0.697, given that our null is true? In order to figure out what the z-score is that corresponds to p hat, or in other words, how many standard deviations p hat is above the mean, we just use this formula. So we take p hat, which is our continuous random variable, and we subtract the mean of that sampling distribution, and we divide by the standard deviation of that sampling distribution. Now, our assumption is that the mean of the p hats is equal to the value of the population proportion in the null hypothesis. So we're assuming the null is true. So we're subtracting p, but p is that assumed p from the null hypothesis. And it turns out that the standard deviation of the p hats is equal to the square root of p times q over n, where q is the, or p is the population proportion assumed in the null hypothesis. Well then, in order to calculate z, we just substitute everything in. So p hat is approximately 0.697. P was assumed in the null to be 0.5. Then over in the denominator, we've got p times q. If p is 0.5, q is the complement of that, which happens to be 0.5. Then we divide by the sample size, 1,228. And then we evaluate this expression on our calculators, and we get 13.81. That means my pictures are grossly inaccurate, but I hope you understand when you see a z-score of 13.81, that is huge. That means that p hat is 13.81 standard deviations above the mean. If you look at this graph, this is 1 standard deviation above the mean. That's 2 standard deviations above the mean. That's 3 standard deviations above the mean. So 13 standard deviations is way out there. So it is definitely significantly high. I think we're going to throw out this null hypothesis, but let's go through the rest of the method and prove that we're going to throw out that null hypothesis. Okay. I'm sorry, guys, I'm having trouble with my cursor again. Sometimes it disappears on me when I'm annotating on a slide. Trying to get it back. Okay. Sorry about this, guys. I can't even pause the recording. Okay, there. I've got my cursor back. Sorry about that. So z equals 13.81, which means our p hat is 13.81 standard deviations above the mean, given that the null hypothesis is true. So I think p hat's significantly high, and we're going to reject the null. But let's prove it using both the p-value method and the critical value method. So first, let's look at the p-value method. In order to do that, we need to determine whether the test is two-tailed, left-tailed, or right-tailed. And in order to determine that, we've got to look at the alternative hypothesis. So the alternative hypothesis says that p is strictly greater than 0.5. Now that arrow points to the right. You can think of it as an arrow pointing to the right. So this is going to be a right-tailed test. Now, since we have a right-tailed test, the p-value is the area to the right of the test statistic. And we can find that area using Excel or table A2. Either one is fine. Now, if I want area to the right of a test statistic, that's going to be 1 minus the area to the left. So in our case, this is the probability that z is greater than 13.81. Or 1 minus the probability that z is less than 13.81. Now, there is no 13.81 on your table because it's so many standard deviations above the mean, but let's look at it. Let's say you were looking for 13.81 for your z-score on your table. Well, the highest z-score on our table is this one right here. Z equals 3.5 and up. We're going to say that the area to the left is 0.9999. Now that's not going to be accurate, but it's going to be close enough for our purposes. So if we're just using that for area to the left, we've got 1 minus 0.9999, which means our p-value is 0.0001. That's one possibility, or we can use Excel. Now I think Excel just gives you a 0 because 13 standard deviations above the mean is just so far out there that I'm not really even sure how many decimal places I would need in order to find that area. So right now what I'm doing is I'm typing equals norm.distribution, norm.dist of, and then I enter my z-score. I want the mean of my standard deviation, or the mean of my distribution to be 0. The standard normal distribution is 0, and I've got a standard normal distribution, so the standard deviation is 1. And the cumulative area to the left, we want to say true because that's what we're looking for. And you just get 1. Obviously, it's not 1. There is going to be some area to the right of that, but it's going to be so small that let's see how many decimal places. Let's see how many decimal places we would need to take in order to get something less than 1. We might be here a while for 13.81 standard deviations above the mean. And maybe we'll be here all day because of the accuracy of Excel's calculation. Yeah, I think I'm going to stop. It looks like at least to however many decimal places that is. Oops. Yeah, all we get is 1 from Excel. So given that, let's go back here. That's the area to the left of 13.81. So the area to the right is approximately 0 according to Excel. Obviously it's not 0, but it's so close to 0 that it might as well be 0. Okay. So using table A2, we get this tiny, tiny probability. Using Excel, we get the closer probability, which is just 0, but just a tiny bit more than 0. So that's our p-value. Now, after you have the p-value, which corresponds to the probability of getting a test statistic that is as extreme as that 13.81 that we got, or more extreme, we want to compare that to alpha, the significance level. Well, alpha is just 0.01, and p is either 0.0001 or 0.000000 for however many zeros that we need. It's going to be a lot of zeros according to Excel. So p is clearly smaller than 0.01. So we're going to reject the null. Again, we're thinking about whether that test statistic p hat, or rather the sample statistic p hat, sample proportion p hat, is significantly high or significantly low. And the test statistic z equals 13.81 tells us that p hat is 13.81 standard deviations above the mean, given that the null hypothesis is true. Like 13 standard deviations above the mean, like 13.81 standard deviations above the mean, that is a huge number of standard deviations above the mean. That is highly unlikely to happen due to chance. So the assumption that led us to saying that that p hat was extremely unlikely must be wrong. And that assumption was that the null hypothesis is true. So we're going to reject the idea that the null hypothesis is true. It's what we call rejecting the null. And then we're going to say, okay, well, what does that mean about the original claim? So let's go back and look at the original claim. The original claim was that the proportion of medical malpractice lawsuits that are dismissed or dropped is greater than 50%. The null was that the proportion of medical malpractice lawsuits is equal to 50%, of course in decimal form. Now we're rejecting this null hypothesis. So what we're saying is sample evidence suggests that that proportion of lawsuits that are dismissed or, dismissed or dropped is not equal to 0.5. In fact, we're sure that that proportion is greater than 0.5, especially since that p hat was all the way on the far right. So we're rejecting this idea that p is equal to 0.5. And rejecting the null hypothesis, in this case, since the claim does not include, the condition of equality, rejecting the null hypothesis is supporting that original claim. So our final conclusion would be that there is sufficient evidence to support the claim that most medical malpractice lawsuits are dropped or dismissed. So there's sufficient evidence to support the claim that P is greater than 0.5, but people don't know about P. People want to hear about the medical malpractice lawsuit. So we want to put it into terms everyone can understand. So we'll say that there's sufficient evidence to support the claim that most medical malpractice lawsuits are dropped or dismissed. That's the p-value method. Now I did the p-value method first because that is the method that's used in most journal articles. Sometimes people won't give you critical values in journal articles, but they will give you p-values. Now p-values correspond to probabilities, so that's insightful as well. So I wanted you to be familiar with this method and be comfortable with the p-value method. But we'll see that the critical value method is equivalent to that. It's just a different way of looking at the same thing. With the p-value method, we're computing a probability, and we're comparing it to that alpha, that significance level, which is also an area in the tails. So we're comparing one area to another area and using that to reject the null hypothesis. With the critical value method, rather than comparing areas, we're going to compare z-scores. We're going to look at our our test statistic z, and we're going to compare it to a critical value z, and we're going to say if our test statistic is more extreme than the critical value, which means it's farther out in the tails than the critical value, then that corresponds to a significantly high or low value of that sample proportion p hat. And therefore, since it's significantly high or low, we can throw out the null hypothesis for rejecting the null, and then we can state something about the original claim. So let's go through the critical value method now. It starts in the same way. We need to determine whether the test is two-tailed, left-tailed, or right-tailed. And we go to the alternative hypothesis to see, to make that decision. So we see that P is greater than 0.5. I always think of this as this little greater than sign as an arrow. Since that arrow is pointing to the right, it's a right-tailed test. Okay. Now we want to find the critical value z sub alpha, or sometimes I'll write z sub crit for critical value of z. This is the z-score that has an area of alpha equals 0.01 to the right. And I want that alpha to be 0.01 area to be to the right because it's a right-tailed test. And the alpha equals 0.01 was given as the significance level in our problem statement. So that's where I got that from. So we've got our area to the right is 0.01. Now I need to find the z sub alpha, or z sub 0.01. That's the critical value. Well, if I'm looking for z sub 0.01, I need to find area to the left, not area to the right, because the z-scores in table A2 or the z-scores given by Excel, both of those involve looking at area to the left rather than area to the right. So we use the area to the right to compute the area to the left. If we've got 1% of the area to the right, 99% of the area must be to the left. We write that in decimal form. And then we can find the critical value of z using table A2. So I want an area to the left of 0.99. So I go over here, and I'm in my positive z-scores table, and I'm looking in the body of the table for 0.99. Oh, I see it. Do you see it? It's the value that's closest to it. There we go. There it is. That's the area that's closest to 0.99, 0.9901. So that's off by 0.0001. Well, the z-score that goes with that is z equals 2.3. This is 2.30, 2.31, 2.32, 2.33 goes with this area to the left. So that's approximately 2.33 as our critical value. Now, if we want to, we could use Excel as well. That requires using this function norm S inverse. Norm S is for standard normal distribution. INV means instead of giving you a z-score, giving Excel a z-score and asking for an area, we want to give Excel the area to the left and ask for a z-score. So we will type that in Excel. Sorry about that. Made it very, very tiny. That's not what I wanted. Let's just delete this column. It's just too wide. And zoom in some more. And I want to give them a probability or an area to the left and find the corresponding z-score. So I type NORMS, INV for inverse, and they're asking for the probability, and that's always the area to the left. So 0.99, or the probability of having a z-score that's less than our z-score is 99%. And so we get this, if we round to 2 decimal places, we get 2.33, which is the same thing that we got using table A2. Okay, so we're there. Now, you've got a critical z value and a test statistic z. The question is the test statistic beyond that critical z value if you were to look at the graph? If it is beyond it, I mean, when I say beyond, I mean farther into the tails than the critical z value is, then we're going to say that that test statistic is significantly high, which means the sample proportion that goes with it is significantly high. And that means we should throw out the null hypothesis, because we've got something happening in real life that is highly improbable to happen, provided that the null hypothesis is true. So in order to figure that out, we need to compare the critical value of z to the test statistic z. Well, the test statistic is 13.81. P-hat was 13.81 standard deviations above the mean. And our cutoff for statistically significant test statistics is only 2.33. So obviously that 13.81, which if I were to graph it, is far off to the right. It's definitely farther to the right than z equals 2.33. So one way that you can compare these is you can take the absolute value of these. Since the absolute value of our test statistic is greater than the absolute value of our critical value, then the test statistic is more extreme than the critical value, which means it's just farther out in the tails, and we can reject the null hypothesis. Another way of doing this is to just graph the test statistic and see if it's in the critical region. That critical z value separates the test statistics that we're going to consider typical from those that we consider to be significantly high. If that test statistic is in that significantly high region, in this case, which we call the critical region, we'll reject the null. So here's what it looks like. I've got my null hypothesis, and then I added this little extra line segment because I want to go 13 standard deviations above the mean. So there's my test statistic, 13.28 standard deviations above the mean. If you're saying, what do you mean? How is it all the way out there? Well, this is 1 standard deviation above the mean. That's 2. There's our critical value, 2.33. There's 3. And we want to do 4, 5, 6, approximately 7, 8, 9, 10, 11, 12, 13, and I guess I overestimated. If that's 14, that critical z value is right there, 13.28 standard deviations above the mean. And then we're saying to ourselves, okay, is that in the critical region? It certainly is. And then think about the probability of getting a z value that's larger than that. That's the p-value. That was nearly 0. And we compared that to alpha, which is the area of all of this when we're doing our p-value method. This area is clearly greater than this area over here. So p is less than alpha, so we reject the null hypothesis. Or we can say this test statistic z is definitely more extreme than the critical value z equals 2.33, so we reject the null hypothesis. So either way, we're rejecting the null hypothesis. And again, we want to state our final conclusion in terms of the original claim. Since the claim was the alternative hypothesis, when we reject the null, we're actually supporting the claim. So there is sufficient evidence to support the claim that most medical malpractice lawsuits are dropped or dismissed. And this is what I was just saying on the last slide. The area to the right of that critical Z value is our alpha value. So this area, which is difficult to draw, like this area here, and then all the way out. Sorry, it's hard to draw it. That's alpha. The area to the right of the test statistic, 13.81, is approximately 0. It's hard to draw that area to the right of this value. It's so far out in the tails, so it's like some tiny, tiny area over there. So you have to imagine that this standard normal distribution is being continued all the way out. Oops, it's hard to draw. But we want the area below that all the way out here, and it's nearly 0. When we used Excel to calculate P, it just had so many zeros. I don't even remember how many zeros it was. It's just a little bit more than 0, because obviously the probability is not 0, but it's tiny, so tiny. I don't even know the order of magnitude of that probability. Sorry, I'm having trouble with my cursor again. There it is. All right. So we see that because our test statistic was in the critical region, so it's farther out in the tails, we're rejecting the null. Well, since the test statistic was in the critical region, the p-value, which is the area to the right of this test statistic, has to be less than the alpha value, which is the area to the right of the critical value of z. So we reject the null. So either by looking at areas, which is what we do with our p-value test, or p-value method, or by looking at z values, so we're comparing that critical value of z to the test statistic z. Either way, we're saying the same thing. We're going to reject the null hypothesis. And I think that makes sense, because if this test statistic z is farther out in the tails, the area beyond the test statistic is going to be smaller than the area beyond that critical z value, which is our alpha value. Or it's alpha if you're in a one-tailed test, and it would be alpha over 2 if you're in a two-tailed test. But still, the principle holds. If your z sub test, that test statistic is in the tails, in the critical region, we're going to reject the null. Okay, so both tests are going to give you the same conclusion. So that's it for that video. I'll see you in the next video to discuss the confidence interval method, and we'll compare that to the p-value method and the critical value method.